welcome back our own David Spivak, talking possibly about the two categories, controls and clones.
Yes, I'm definitely going to talk about that. I'm also going to start us off with like a general look at Poly again for people who might not feel motivated right away. Because what I want to start with is like some very simple things, undirected wiring diagrams. Directed wiring diagrams, and then we'll move into comonoids and then control and stuff like that. But I wanted to start here because I think this is just a very simple story for people who are like don't know so much about polynomials. So a polynomial is, you can think of it as a typed finite set. But it might not be finite, but kind of a set of sets. So you could think of it like a bundle. But we're going to think, but for the purposes of wiring diagrams, we're going to think of it as like something with, these would be like the positions of the polynomial. A polynomial is actually a sum over some positions of y to some direction. So for example, like y cubed plus 3y squared plus 1 would have 1, 2, 3, 4, 5 positions. And the first position would have 3 elements, 3 directions. The next one would have 2, then 0. So a polynomial functor is one of these. But for the purposes of this talk, to connect with things that we're doing with the Mozilla project, things that we're doing with I've done with Brendan in the past, I want to think of it as a typed finite set. And it might not be finite. There might not be 6 positions like there are for this one, or 5. There might be infinitely many. But we can draw it like this. And then a map from P to Y is a global section. So if you don't know polynomial functors, this is just a natural transformation from P to the identity. But in terms of these pictures, it would be like a global section, meaning like some way of selecting a single thing from each fiber. Yep.
When you draw that circle with lines coming out of it?
Yeah. This one would be typed with 3. This one would be typed with a 4-element set.
I see. Okay.
Sorry, that's messy, but yep. So every wire here would be typed with a finite set.
So,
and
so you mean
a set
typed in finites?
A set of sets. So it's like the positions of the polynomial would be the sets, or the wires coming out of a circle, and the what is each wire labeled with would be labeled with the directions there.
I was thinking it was the set was the total space typed by the positions.
No.
Okay.
Yeah, no, more like this. So then a map from P to Y would be the product, the set of polymaps from P to Y, which I often write gamma P for global sections, is the product over all of these wires, P and P of 1, of the directions at that wire. So it would be this times this times this times this times this. Why would you want to do that? Well, in previous work with Brendan and others, like we thought about wiring diagrams that looked like this, where you would maybe put like a span. And every wire is labeled with some set, and you might put a span into each of these things and get a span for the whole thing. So you could query, you could put relations into each thing. If you said, okay, this thing, like I'm going to make a relation on integers times reals times string, and you have like reals, integers, and strings, and you start like saying like it's taking down some data, you could pop that whole database into here, pop that, or that whole table, put a whole table into here, and put a whole table into here, and this would give you a query. So I wanted to say, to start off the talk, I wanted to say like, well, this sort of thing is very much a poly sort of thing to do. What it is it's going to be a map in what we're looking at here is cospan poly. That gets at the entire story of cospans of typed sets. So what does one look like? It looks like if I drew this wiring diagram here, I would say P1 plus P2 plus P3, because there's 3 little circles inside, a map to some junctions, and then some P prime, which is this thing outside. This P prime is some polynomial with 4 positions. This polynomial P1 has 3 positions, this one has 4, this one has 3. And this map says that every little string in P1, every little string in P2, and every little string in P3 needs to go to some junction, one of these points here. There needs to be a map on the types. And every one of these outside things also has to go to one of these junctions. And so this data is exactly the data of one of these in terms of the strings and the things that they carry. And so if you wanted, for example, the algebra of spans, then you would be looking at, well, we can talk about that if people are interested in this. But like, you can talk about these algebras of spans as for every polynomial, for every object in here, you associate like choose the set of all pairs of an S and an F, where S is a set and F takes P to Y to the S. I don't know whether I should go through this, but what I think I'll go through it better. I'll go through the next one in more detail because it gets towards this control thing. But what I wanted to say at this point is just that the whole story of wiring diagrams and how they work is all captured by kind of this poly story. They're really, each of the strings are positions. This map says that the positions in here need to go to the positions on the junctions, and the positions outside need to go to the positions on the junctions. And the maps on the type finite sets work out so that you can actually carry relations on this side to relations on this side using the usual push-pull thing. So I'm happy to go over that either in the questions or now. But what I want to move towards is the next kind of wiring diagram, which is the more controlling kind of wiring diagram. This is more relational type wiring thinking, and we're kind of moving towards control thinking, not because control is better, but because it's the part of the thing we're going to talk about today. So I'll just move into that. So there's another kind of wiring diagram where you have inputs and outputs on each of these things, and some kind of thing like this. And again, we can do this with polynomials. So this will be a polynomial. This will be a pair of polynomials, one for the inputs in and one for the outputs, and P2 in and P2 out. And then this whole wiring diagram will be some P prime or maybe Q in and Q out. And OK, so what am I talking about? Well, let's say you want to say that I'm looking at this thing, and it has 3 wires, and this wire is carrying integers, and this wire is carrying integers, and this wire is carrying reals, and it's got an output that's carrying Booleans. Then the polynomial I'm talking about here is y to the z plus y to the z plus y to the r. And the output polynomial is y to the bool. And if you look at the global sections of this, the polynomial maps from p to y, it would be z times reals. It would be the triples of things coming in. What's coming into this box? 2 integers and a real. So the set of things that are able to come in is exactly the global sections of this. And the set of things that are able to come out are exactly the global sections of that. So if this is P in, and this is P out, then what is this wiring diagram? Well, let's say P in is P1 in plus P2 in. That means that the total number of strings of some box, I'm going to take P1 in, and P2 in, and I'm going to add up their positions. So now I have 4 instead of 2 and 2. And my outputs, oh, I made everything have exactly 2. OK, let me not do that. My outputs on P1, there are 2 of them, and on P2, there are 1 of them. So P2, P out is going to be P2 out plus P1 out plus P2 out. So I'm forming this new box that looks like that. And now I can't tell. It has 4 inputs and 3 outputs, and each one is labeled by like some set. And so Q is this big thing, and a map from Q out to P out says that for every output wire of Q, pick which output wire of either P1 or P2 you want it to be feeding from. And then tell me how anything that's fed through can like get translated like any direction, any element coming out of this, like a Boolean, gets translated to that one. It might be a function. You could restrict this to be what's called a Cartesian map if you want these wires to carry a single type. But in general, what they're going to do is allow a function to take place as you translate through the wire. And so this diagram here says, first of all, for every output of Q, tell me who's feeding it. And second of all, for every input of a P, this one, this one, this one, or this one, tell me who's feeding it. And who can feed it is either a P out again. So this one is feeding this, and this one is fed by this. But some of them are fed by Q ins. And this data tells you all of the type finite set or finite set, like all this typed information in one big thing. And so how do you convert this? But that's not how we usually use polynomials that's not the way I usually use polynomials. Usually I'm not using polynomials to specify all the little pieces here. I'm usually just using them in a different way. I don't know if you don't know my work very well, that's completely fine. I'm just saying that that's not how I usually use them. And so it could be confusing for people who have seen me talk about polynomials before. But this is holding all of that data. And the way you get from that data to the usual way we talk about these things is you take this really complicated looking thing, global sections of P out, y to the global sections of P in, mapping to global sections of Q out, y to the global sections of Q in. So let's say you had this data here. You knew how every output was fed by some output of P, and you knew how every input of a P was fed by either an output of a P or by an input of Q, something here. How would you get this kind of crazy information? And what does this even mean? Well, in our case, if this was integer, and this was a real, and this was a Boolean, and this was a string, then global sections of P out would be reals times Boolean times integers. It'll be the product of everything that they're sending out at any given time. That's global sections of P out. And global sections of P in is the product of this, 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 and this, which is z times z times z times z times bool times string. And this thing is going to tell us, given an output of given an output of the P's, I get an output of the Q's, and vice versa. So how this works is you just, let's see. To give a map like this, for every map from P out to Y, global sections of P out means polymaps from P to Y. And so if I had a polymap from P out to Y, I would get a polymap from Q out to Y. And that gives me, for every one of these, gives me one of these. And if I further had a map from Q in to Y, I had a little map from Q in to Y, and I already had my map from P out to Y coming from that thing, then I'd get a map from this whole sum, which is a coproduct, to Y. And so I'd get a map from P in to Y, which is what I'd need there. So I don't know if that was a lot. It might have been a lot, but what I'm saying is that this data, which is very much just like a picture of a wiring diagram and how the data flows, if you just hom out into Y, you get this sort of thing. And this is telling you about the actual data that's flowing itself, not how it's arranged into wires. And the reason we might like this is because it's at this point that we can start talking about dynamics. If you have like one polynomial, this thing, mapping to another polynomial, then if you have any dynamics on this, you should get dynamics on that. And the way that happens is if you have a state machine running this one, what this says is for every state, give me a global section of P out. So if you had this guy was in some state, for every state it could be in, tell me what the real and the Boolean is putting out are right now. Sy to the S to by to the A is the same thing as two things, a map from S to B and a map from S times A to S. So it says for every state, what should I output? So given a state, give me a real and a bool. And for every state and input, give me a new state. And that's what this data right here is. So this data is a state machine running on the P and this one, the two P's. And then from this, I get a state machine running on the Q, because I can just compose. OK, questions?
Maybe
Yeah.
this is where you're going,
Yeah.
but what if instead of a box being a pair of polynomials, what if it was a polynomial sitting over another polynomial?
That wasn't where I was going, but it might work. I don't know. Does that work?
I think so.
Interesting.
I talked about this with David Jasson.
Oh, okay.
And you at ACT, I think.
OK. Yeah. So, but any questions about this?
You could make it
Yourself?
way more confusing by writing gamma p in as y to the p in, and then it would be like y to the p in.
Yeah, except y to the p in, yeah.
That's not really,
Because polynomials do have exponentiation, and that is, so y to the p in of 0, yeah, is what you want, yeah.
0, not of 1.
Of 0 is, sorry, 0 is a polynomial, is the initial object. It's the 0 polynomial. And this is polymaps from 1 to y to the p in. And that's p in polymaps from p in to y. OK.
What is evaluation of the polynomials?
Oh, yeah. What is this? So this is the exponentiation in poly. This is the Cartesian closure. There's a closure for times. And it's like, it's kind of a weird thing. And I don't know if we really need to talk about it.
It's kind of weird because it's not 0 to the p.
Yeah, exactly. Yeah. This symbol is the symbol for exponentiation. And once you allow yourself to use this symbol, then you no longer have the property that evaluating means plugging it in for every instance of y. So
and I
yeah.
guess in particular, that's a completely different meaning of the exponential than when you're putting a set.
Which is the exponential in set, right?
What?
Right. It doesn't-
The exponential in set is, yeah. So a to the b, this is the exponential in poly. If you take the two set polynomials, this is this, you get the right answer. It's a set of maps from a to b. This thing is the usual. This exponential thing works correctly in every sense except for the plugging in sense. It's the Cartesian closure. You look confused. It is curious. Like y to the.
Endorse that notation?
I mean, well, you need some notation for exponentiation, like the internal.
The arrow object for.
Yeah.
Because the,
Well, there's many different closures. There's ones for times. There's one for tensor. But the one for times, I just followed the notation from sets or whatever and wrote
you're
a to the b.
using that sort of thing for-
Well, it does work in all cases that we already had. Like if you say y to the b, it does work. Yeah.
Except for the evaluation. Why doesn't it work for, I don't know, maybe this is too far.
I
But
didn't
Yeah.
mean to cause this whole
That's okay.
aside, although I'm slightly confused.
yeah,
So p to the q, composed whatever r, is not guaranteed to be p composed r to the q composed r. So if I evaluate like y to the y at 5, I'm not promising that that's y of 5, y composed 5 to the power y to composed 5. That's kind of like a, what's that, freshman, whatever thing? Freshman stream, yeah. Okay, but yeah, happy to talk about exponentiation. I'm not sure if the notation is great, but it's just the fact that you shouldn't expect that p to the q composed r should be that. Okay, what I wanted to talk about was that wiring diagrams, no matter how you get them, whether you get them from polynomials, like the fact that so much of algebraic Julia, like a lot of it is based on wiring diagrams of different sorts, or I guess it's the algebraic dynamics package. But all that stuff has typed finite sets, I imagine, in there, and you can just arrange that using polynomials. And all the things that we need to do in terms of the algebras like this one are completely polynomially describable. But what I wanted to get to was like, what are we really seeing when we get to this point where we have a dynamical system running on one of these boxes? And what it turns out is that like sy to the s, the thing that makes it work, if I now go to like p, I'm going to call this whole thing p, which is an abusive notation in the sense that it's not an abusive notation because I'm throwing away all the notation we've used so far. Like I'm not going to be referring to these boxes anymore. I'm just going to be referring to polynomials as like interfaces for dynamical systems. So this thing is becoming p, and we're kind of going to leave the old p's behind. What is it about this that works? P, if it was like, say, by to the a, would be a machine that's outputting b's and inputting a's at this stage now that we've taken kind of global sections of the old stage. We're now in this world where we've got something that's outputting b-ish stuff and inputting a-ish stuff. And what it says is that for any state of a machine, that state, I said it here, that state outputs a b, and then given an a, updates the state. And it just kind of runs for, but what is it about that makes it run forever? And what makes it run forever is the fact that sy to the s is a comonoid. It's that kind of comonoid, meaning in Haskell they would call it the store comonad. It's a comonad on sets or on types. It contains a map from sy to the s to y and a map from sy to the s to sy to the s, composed sy to the s. So it's got like one of these things and one of these things, if you like diagrammatic pictures. And they compose associatively and all that sort of stuff. And the reason that makes this work is that you have sy to the s to p, but then from that you get a map from sy to the s to sy to the s, compose sy to the s. And then you can run phi again on itself and get p composed p. So this says if I have a state, I get the output, and then for any input, I get a new output. And then for any input of that, I can update the state. And you can just keep doing that to your heart's content. Sy to the s compose itself 50 times, and then run phi compose with itself 50 times, and get p compose with itself 50 times. And you can see this is kind of the easier version of something that's much more interesting and something that Sophie and I are working on. But this is saying that given a state, I can see its output and run that 50 times and stuff like that. And just indefinitely if you want instead. So what this is really about is the comonadness of sy to the s. And even going further, there is a co-free comonad construction that says if you have any polynomial, you can turn it into a polynomial comonad, and you can turn any polynomial comonad back into a polynomial. You just take the underlying thing. So if I have a polynomial comonad, some c and a map from c to y and a map from c to c composed c, and then I can just forget this structure and get the polynomial back, this polynomial c. And this thing here is called the co-free comonad. And so you can take any polynomial and get the co-free one on it. And this is a right adjoint to forgetting. And so what that means is if I have any polynomial comonoid, sy to the s, say, and a map from that to p, that's the same thing as a map from sy to the s, a comonoid map to cp. And finally, we're in the world where we can start to just think of everything that we're going to be talking about today as comonoids and their maps. Polynomial comonoids are very interesting, and one of the most interesting things about them is that they're exactly categories. So polynomial comonoids are categories. You look at this data of a polynomial and a map to this and this, and you think, why would that be a category? But Priya's explained this before, and it's a result of Aman and Ustalu that these are exactly categories. And these things, maps from sy to the s to cp, are exactly, these are in one-to-one correspondence with cp sets. Functors from this category to set. So this thing is a category. Oh, sorry, with elements s. Thank you. So for any functor from a category to the category of sets, you can take its category of elements. And those elements, those are like an element would be an object in this thing and an element in the set that it's mapped to. And those are exactly these things here. So what we're moving towards is to examine just the category of comonoids and their maps. Because it turns out that these are, the reason we're looking at these is because they're kind of controllers. And so that's what we're going to get to next.
Why do we start with undirected wiring diagrams?
We started with undirected wiring diagrams because I wanted to bring people in who hadn't, I wanted to talk about poly in general a bit. This is definitely like a vignette that is not really part of the story. It was like this little vignette, and then this one's more part of the story, and then we're moving into just control. But I was partially talking about this just because, I don't know, we've done work on this together, Brendan, and I was just thinking like, oh, this whole story of typed finite sets used to kind of feel more mysterious, and now knowing that it's just co-span poly felt like we could, I don't know, it felt like an interesting point of view that I don't think we've talked about in this seminar before. Like,
The fact that you just said about comonoid maps didn't depend on the codomain being covariant, right?
it did not, right?
Just
Yeah.
the domains discrete.
Yeah. Okay. So I want to talk about comonoids in poly. And we've talked about these before. They're categories. But the maps between them are what are called cofunctors. Now, the maps between them are comonoid maps. You have C and this like thing like that, and like that, C to C composed C. And you have D and D's things like that. And you can write down what a comonoid map is. It's a map from C to D such that like if you go to Y on either side, you get a check. And if you go to C, D, and C composed C, and D composed D, and these are these, and these are this, and this, and phi, and phi composed phi, that these work out. So it's the usual kind of a way of going from C to D, such that if this is the same thing as this, and this is the same thing as this. So C, D, D, D is the same thing as C, 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 D, D. And that's what these two things say. So it's a usual notion of what is a comonoid map. But if comonoids in poly are categories, then what are these weird comonoid maps? And it turns out that usually people think about categories and functors, but here we're thinking about categories and cofunctors. And so cofunctors are not a usual notion people think about. But I want to just give you an example or two. So for example, you might have the category of that indexes reflexive graphs. So a functor from this thing to set would be a reflexive graph. So you have a bunch of edges, a bunch of vertices, a source, a target and like a reflexive edge or something. Sorry, that says refl on it. And a model of this, a functor from this to set, would be some picture of like a bunch of dots and arrows between them, and maybe like that. And every arrow would have like this reflexive edge sitting on it. The specially chosen edge that was the reflexive edge. So there V would be sent to a 4-element set, etc. There's a cofunctor from that to this guy that just forgets. Okay, so what is a cofunctor? What is a cofunctor? A cofunctor, C to D, consists of 1, a function ob C to ob D, 2, for each C in ob C, and F okay, so what I need some notation. C bracket C is going to be the disjoint union over all C prime in ob C of C maps from C to C prime. So this thing means I have a category, I've got an object in it, and I want to look at all of the outgoing maps. So what's an outgoing map? To pick an outgoing map, you pick a codomain and you pick a map to it. So C bracket C just means all the maps coming out of this object C. And so what I'm saying here is a cofunctor says for every object of C, give me an object of D. And for every morphism coming out of that object in D, a morphism like F sharp of F, that's an outgoing morphism from C itself. So it says, for every object upstairs, give me an object downstairs, and for every arrow coming out of it, tell me a lift of that arrow. Now, how do those lifts work? Well, first of all, such that, or preserving identities. That's what this guarantees. So if I took an identity here and I lift it up, it better be the identity. Codomains and compositions. So if I have an object up here and I come down, I send it down here, and someone picks a map out, I pick a map out. If they pick the identity, I pick the identity. If they pick anything and I pick the map out, the codomain matches. And if I compose, then running it twice, I get the right answer. Composition lifts up to composition. So that's what a cofunctor is. And then that is exactly what this data controls identities, this requirement, and this check mark here, this requirement, controls compositions and codomains. So I want to talk about how that feels like control. And I want to talk then about what natural transformations are between these things. And so you get a whole monoidal category of controllers for any two categories. One category can control another. And what that's talking about is that in the category of comonoids, there's lots of relationships between comonoids. And in general, the bicomodules, which I draw this way, are arbitrary data migration functors. These are ways of taking any data on D and getting data on C. And those are like a very big class of things that we talk about here a lot. They move D sets to C sets. But inside of that, one special way that something can get data from another thing is control. So if something is controlling something, then they exchange data in a certain way. And so what I want to talk to you about is how cofunctors are like control, how it's a very small but important part of the category of all ways of translating between two things. And then talk about natural transformations and some monoidal category stuff that you get. Yeah?
And this category, so with the directed wiring diagrams, there are relations, and when you say control, you mean like providing input, like driving a system by providing inputs to it, is that right?
Yeah, what do I mean by control? So what I mean by control, so cofunctors represent control. So if I have a cofunctor from C to D, by which I mean just one of these comonoid maps, then D is controlling C via F. So why would I say it that way? Here's what happens. Every object of C, think of it as like some position of some system. And the first thing it does is reports its position to D, and D is like getting some view. So let's say C is like your submarine, and you're inside the submarine at the control panel. And so there's all sorts of stuff in the environment of the submarine that you can't see, but you see a radar and a sonar, or whatever you see, maybe a sonar and like some stuff, right? And you see some dashboard of things, and that's what you're seeing. And then in your little control room, you move a lever or you press a button. And those are the outgoing morphisms of your object. So you've got some, so like the real situation is some object in some position in C, some object of C. So C of 1. That's how that corresponds. So you have some real situation, and it's sent to some like image in your control room. And now, given that image, there might be certain buttons that are not pressable. There might be certain things in your joystick you can't do. But there's other things on your joystick that you can do, and other buttons you can press. And those are exactly the outgoing arrows of your object. So all the things that you're allowed to do, all the ways you're allowed to jump forward, are the morphisms out of this thing. I could do that, I could do that, or I could do that. Once you pick one of those things, one of those controls, it's sent back to C as a controller, as a move that happens actually in the submarine itself. Some engine actually gets turned on or whatever. And this thing is so well controlling that if you did two things in a row, you could know kind of what the control on C was going to be just from D. So these are very like idealized and perfect controllers. They do what they said they're going to do, and they compose correctly. And so these are the vertical maps in a double category that has a lot of what we do here at Topos in it. These kind of data migration functors. These are very simple in this equipment. These turn into adjoint profunctors or adjoint data migration functors between C sets and D sets. There's a way that you can use this to take any data that D understands and turns it into data that C understands, and vice versa. So I want to say that amidst all the cool stuff that you can do between categories, one of the simplest things is this notion of control. And so let's say cat sharp, instead of cat, which is a category of categories and functors, cat sharp is going to be the comonoids in Poly. And it's going, in other words, categories and controllers. So let me give another example of this. Suppose that, so there's something called the fundamental groupoid of a space. So if you have a space X, then the fundamental groupoid, you can learn about this in an algebraic topology class. So maybe your space is like this. And the fundamental groupoid is a category where every object, every morphism is an isomorphism. So the objects of this category are the dots, are the points in X, all the points in X. And a morphism in this category is a path from one point to another up to homotopy. So this one and this one are the same, but they're different than this one because you can't continuously deform one to another. So the objects are the points and the morphisms are the paths up to homotopy, and you can compose paths, and every path is invertible because you can just go forward along it and then backward along it and then slurp that back down to the identity. Okay, so that's a fundamental groupoid. What is a cofunctor to the monoid of time? So this would be like a time control on your space. If this is always D control on C, this would be like time control on the fundamental groupoid of your space. What would that mean? To have a cofunctor like this, every object here would go to an object here. Well, this category is a category with one object. It's a category with one object, and it's a monoid, the monoid of time. And so this cofunctor would say for every dot, I need an object. Well, there's only one object. And for every outgoing arrow, which is an amount of time, tell me what happens. How does that control or move what's going on here? So it says, so a cofunctor like this would say for every object and every amount of time, tell me a path, an arrow coming out of this thing. But only up to homotopy. It's just a path up to homotopy. And yet, it really is a real path, because if you can say, here's where it is at 1, here's where it is at time 2, here's where it is at time 3, here's where it is at time 4, and time -1, and time -2. But I can tell you what it is at time 0.5 and 0.01 and stuff like that. And if I tell you what it is at 0.01, and then I move a little bit to 0.03, like the compositionality of this there makes sure that this is all coherent. So in fact, for every point, I can say an actual timeline, even though it's in categories, even though these are homotopy classes of maps, I actually have the time.
Basically, because you have a codomain of the homotopy class for each time. So
That's exactly why. I have the codomain for the homotopy class at each time, and so I actually know where it lands. So it's kind of surprising. Inside of this homotopy, very homotopical thing, in functors you can't find, that homotopy is kind of lost forever. But in cofunctors, the homotopy equivalence relation has killed something. But in terms of cofunctors, it hasn't killed things. So these are like flows through the category, time flows. But they're really like time controls. Time is controlling you. It's pulling you along. So the next thing I want to talk to you guys about is the natural transformations between these things. And that's, I guess I won't have much time beyond that. So what is a natural transformation between these things? There's two ways you could talk about what a natural transformation are. There's two formalisms you could use. And I used one of them and was thought I'd found something new, and then it turns out no, just looking the other way, and it was already well known. In one of them, you could use kind of the double category theory. Maybe I don't have time to really go through this. In the other one, you use enriched category theory, and basically what a cofunctor natural transformation is you have two maps from one category to another, two cofunctors, phi and psi. And what is a natural transformation between them? What it basically does is for every object in C, it goes to some object in D. Every object in C is sent to some object. Sorry, what are we talking about? So phi sends each object in C to some object in D. Alpha will be a map from C to Y. It'll be a global section. So throughout this entire talk, even back in the wiring diagrams part, we were talking about maps to Y. Maps to Y are global sections. And what is the global section of a category? It's a choice for every object of that category of some map out of that object. So it's for every place you could be in the world, what are you going to do right now? So it's a dynamical system. It's you've got this category, and for each object, you pick an arrow out. It's some way of moving through categories. So when people talk about category theory in Evans Hall and Berkeley or anywhere around the country, they're almost always thinking categories and functors. And there, categories, you're not really thinking of moving through categories. But in this comonoids version, what categories are for is not for holding data, like all the maps between this abelian group and that abelian group. What categories are for here is for moving through some space. You're at an object and you're about to go forward to some other object, and that you have the objects are the positions of the polynomial. The maps out are the directions, and then that's kind of the whole story. You might land somewhere, but that's kind of an afterthought. Where you land, codomain is like an afterthought in some sense. How you compose is the next step. But anyway, so what is, if you have two different control ways that D can control C, what is a map between them? A map between them is for every object in C, some choice of map out, such that if you look at the first controller before you did this, and you look at the second controller after you did this, you get the same answer. So it's like the person D has two different controllers, and C is able to transform itself and change so that it can look from one perspective the way that it looks from the other perspective. So this C looks to D like that under phi. Under psi, this one looks like D, and alpha C is the natural transformation. It says I can change myself back, outside in a way that's imperceptible, like makes these appear the same. Yeah.
Can I understand better the way you're using the word controller?
Yeah.
Because there are two, like if you imagine like a keyboard or a video game controller, right?
Yeah.
There's one aspect of the controller which is just like the buttons
Mhm.
you press given each state,
Mhm.
whatever that means. And there's another thing which is what the buttons do when they actually
Yeah. Yeah.
in the
Yeah.
other state machine.
So let's say we've got this. Yeah. We've got this.
Controller.
Yeah. Both. So let's say your machine. Does your machine always have the same buttons, or does it only have?
Let's say the availability of the buttons depends on the state.
Okay. Well, right now this thing only has 6 buttons, 1, 2, 3, 4, 5, 6. But maybe like it's got this other button that like can be depressed. Like in certain cases, this button like doesn't work, right?
Doesn't exist.
Doesn't exist. It's like pushed down already or something. So so this would be like y to the 6th plus y to the 7th, because sometimes I get this last button also.
Right.
And for every object in C, I get either y to the 6th or y to the 7th, meaning either I'm in this state or this state, and if I'm in this state, these are the 6 buttons I can press, and they'll cause a change in the system or whatever. But this is not a category. This is just a polynomial.
Right.
But there is a corresponding category, namely the co-free on this. And you get an automatic cofunctor to that guy. So this thing is what I would be saying is really controlling it. This thing is something that is in 2 states. It's either like big or small, like it's either this one or with this one. And then 7 cases if it's big, and 6 cases if it's small. And it's just this infinitely, this tree, all possible trees. Yeah, the trace of a plan of using your controller. Yeah.
So when you say controller, sometimes it seems you mean like the cofunctor, and sometimes you mean the co-free.
This one is the thing that's controlling. This is the sense in which it's controlling. This is the controller. This is the control
Mechanism or something.
mechanism. Yeah,
Right.
yeah.
But it seemed like you were saying controller for the control mechanism.
I may have accidentally. Yeah, yeah.
Okay.
Yeah.
That's just.
That was just a typo,
Okay.
speecho. Yeah. So we have this control mechanism, and this control mechanism, and C has this way of doing something where under one control mechanism, you get the same answer as if it did this thing and then looked and then the other control. But it's not just that like the way it appears to D, like whether this button is depressed or not, is showing up, but also for any map out of that, if you chose a map out to some other object, in other words, you chose a control move, then the way this would be updated when you lift it, if you then applied your alpha, would be the same thing as if you did your alpha first and then lifted. So in other words, to D, the change here is imperceptible. D using phi or D using psi, they agree as long as alpha is allowed to do its move in C first. So this goes here and this goes here. This sort of picture looks almost exactly like what the natural transformation picture looks like. It's just upside down. Okay, so what I'm saying is that cat sharp from C to D is actually a category. Cat sharp is a 2 category. The objects are categories, the morphisms are controllers, and the natural transformations are flows.
Morphisms are control
are the natural.
Sorry to slip
The
in.
morphisms are
I
a
don't mean to be
control.
pedantic, I just-
The morphisms are control mechanisms, and the two cells, the two morphisms are like these flows that, like, say every object in C can move to something else where they agree, where you see the two sides. And now I guess what I was going to end with, but maybe there's not really time, is there's two different sorts of things you could put into D where this category becomes a monoidal category. And they're kind of interesting, but I think in the interest of time, I think I'll just stop here.
In one sentence.
Yeah, in one sentence?
What do they mean?
Yeah.
Reductions of parallel control.
Okay, in one sentence, what do they mean? So,
Feel like, I guess.
yeah.
Or even like literally what?
Oh, literally. Okay, literally, if M is a times monoid, then, in other words, if I have a map from M times M to M, I use just juxtaposition, just like in polynomial notation, to means times, and 1 to M. Then, well, I always have a map from any object, any polynomial, to the polynomial times itself. And so if I had two different maps from C to M, then I would get two different maps. Then I'd get a map from CC to MM, and then I go to M. So that's one. If T is a tri-monoid, is a composition monoid, a monad, so we have Y to M to T and T composed T to T. Then since C is a comonad, I have this sort of thing. If I had phi1 and phi2, and then I could go to T. So I know that's very, very fast, but like there's two different ways that you can, and so if I had cat sharp, so cat sharp C cofree on M, and cat sharp from C to cofree on T are monoidal categories. And they are pretty interesting. Let me tell you what this one feels like. So this is a monoidal category. T is a polynomial monad, like lotteries or lists or something. So let's say T is lotteries, meaning a lottery is you choose some number of tickets, a natural number. You choose a distribution on that set of tickets, like 1/3 chance of the first ticket and 2/3 chance of the second ticket, and then you choose a ticket. Okay, so what would this be? This is a monoidal category. What it says is that for every object of C, you've got this space, C, and it's being controlled by lotteries. What does that mean? It's the set of all ways C could be controlled by lotteries. You've got this category C, maybe it's the fundamental group of a space. It's the sort of thing you're going to move through, usually. Okay? So what does it mean for C to be controlled by lotteries? It means that for every object of C, you choose a lottery, maybe 1/3, 2/3. And then for every ticket, the 1/3 ticket or the 2/3 ticket, pick a morphism out of C. So if T was Y here, instead of lotteries, it would say for every object in C, pick a morphism out. That's just dynamics. Every point gets a path out of it. But this is saying, no, what I want you to do is for every point, pick a lottery at that point, like 1/3, 2/3, and then for whatever happens, pick a way out. And that's a monoidal category because if I have two of them, I could say, what would I do? So I have my object, and I have this for every, I have a lottery, I have a choice of lottery on it, and another choice of lottery on it, because I have two objects in here, and I want to tensor them together. So for every object in C, I have two lotteries, the first and the second. So what do you do to multiply them? You take your object in C, you run the first lottery, for every possible ticket, like 1/3 chance or 2/3 chance, you go where it says to go, and you'll have your second lottery sitting there, and that's when it's like 1/6, 1/6, 1/6, 1/6, and for each of those tickets, each of those 1/6 chance die rolls, you have a path out of that one, And so what do you get? You get this big lottery of 1/3 times 1/6 plus 1/3 times 1/6 plus blah, 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 and 2/3 times, I don't know, 1 in 52 plus 2/3 and 1 in 52, or whatever happened for your second lottery at the second position you landed at. And you have that, you consolidate that into one big lottery with like 58 tickets or whatever it has in it now. And for each one of those, you get a composite morphism out. And that is a monoidal structure on this. So, okay, thank you.
We sort of already had the what would you say if you had more time question. So other questions, comments, issues, troubles, or fears?
Yeah.
Are there categories enriched in cat chart?
So categories enriched in polyop are basically like bunches of categories with for each one a data migration between them for every pair of. In polyop you have a bunch of objects. For each object, you assign. Yep.
A single object.
It'd be like a network of O-logs. So it'd be like every person gets a category, and for every morphism, you get some data migration. A category enriched in cat sharp. I just said what I knew instead of answering your question. I did the question transposition, whatever it's called. I don't know what a category enriched in cat sharp would look like.
Maybe a single object category enriched in cat sharp would be a category with a comonad on it?
Yeah. Yeah, usually if you run comonad, category enriched in cat sharp, not cat sharp op. Yeah.
Or maybe you have to off.
Yeah.
Normally
I don't know.
If you run comon twice,
then you kind of get comono again-ish. Like identity on object. I don't know. You don't get much new. But yeah. Category enriched in cat sharp, I don't know what that would be. Yeah.
These very cool time controllers on like the fundamental groupoid.
Oh, I forgot to tell you what a natural transformation between them is. But yeah, it's like a homotopy.
Great.
Yeah.
That was
Or
what I was gonna
yeah, what were you going to ask?
Interesting.
Yeah.
There's no continuity built into this, right?
Yeah.
Can I like?
There's no continuity built into it.
I have the same question, every time. Like, can I just do this in like a topos of spaces? Or, like,
So yeah,
this be
so poly is the category of connected limit preserving functors from set to set. As you and Simone Henry pointed out, if you look at pullback preserving functors from set to set, then comonoids are all Grothendieck toposes with enough points. So instead of thinking about like pre-sheaf toposes, we should be thinking about general, like probably poly was the wrong thing, it was just easy for me. And it's really good for computation. But like for a mathematician who wants continuity, you probably want pullback preserving functors instead of connected limit preserving functors. And now everything's just about sheaf toposes with enough points.
So like instead of y to the r, which is not topological, you might really want the topological monoid?
Yeah, you might really want the topological monoid, yeah.
Great.
Yeah.
Thank you for explaining
your own work to you? Yeah.
Why this
why your paper might be of value or something. No, yeah, I think it's really cool. Yeah, Kevin answered a Math Overflow question of mine that I think is really, really nice.
It's great when you ask anyone in the lab and they turn out to be
Yeah. Well, yeah, but it's not a coincidence that like the guy with 55,000 Math Overflow points happens to be here. I mean.
No, I think you're thinking of my MSc score.
Oh, okay. Yeah.
Other questions?
Other questions?
We can certainly chat more across the hall over a tea, but let's thank David again for now.
Thank you.